Welcome. I'm Randy Anderson, the chapter president for Sacramento RTB, and we'd like to welcome you here to our meeting this month. We're really delighted to have Dr. Leslie Wickman with us. She is an internationally renowned research scientist, engineering consultant, and she'd earned a master's degree in aeronautical and astronautical engineering and a doctoral degree in human factors and biomechanics, both from Stanford University. Dr. Wickman worked as NASA's Hubble Space Telescope and International Space Station programs, receiving commendations from NASA for her contributions. She also has worked on special projects, including technical and or policy aspects of national aerospace and defense issues, including climate change impacts on national security and future human spaceflight missions and technology, and has lectured around the world on astronaut training and operations, environmental stewardship, and the interface between science and theology. She was the former executive director of American Scientific Affiliation, now founder and director of her nonprofit, Starry Nights Incorporated, both organizations devoted to the interface of science and Christianity. Additionally, she directs Biola's corporate affiliates program, running a Templeton grant to support women in STEM fields, and serves as a Reasons to Believe visiting scholar. And of note, she also helped design and program the Bellagio fountains in Las Vegas, which is pretty amazing if you've seen those. It's quite a work of engineering and art. And she also she's a professional athlete and a former women's professional tackle football player, earning all conference recognition, and helped her team, the California Quake, win the Women's World Bowl. So Leslie is quite the Renaissance woman here. So we're delighted to have her come and speak to us today on is the planet Earth just a lucky accident? So Leslie, thank you very much.
Well, thank you so much for that warm welcome. And I know when people read my bio, they always think that I've done a lot of different things that are not necessarily connected to one another. And I explain it by the fact that as a kid growing up, I had a pretty healthy dose of FOMO, or fear of missing out. So I had to try a little bit of everything. So life's been an adventure. And yeah, this is one of my favorite topics to talk about. It seems to be something that people are very interested in, especially with our culture that is more or less fascinated, if not downright obsessed with science and technology. So I've had conversations with people on the chairlift while skiing about the Anthropic principle, and it's just something that I think is really accessible for people, and they seem to really enjoy talking about it. So I should give some credits to a variety of sources that I used for this presentation, including NASA for a number of the photos. My friend Ron Cottrell, who wrote a little coffee table book many years ago called The Remarkable Spaceship Earth. Mark Ritter, who you might know, he's an RTB guy, volunteer at swordandspirit.com, John Bloom at Biola University, and of course, Reasons to Believe, and all the scholars there that have contributed a lot of the facts that I'll be presenting tonight. So for me, my personal interest in science and faith started with my dad's backyard telescope. I grew up in the rainy Pacific Northwest, and so I have especially fond memories of the clear nights that we had in between all those rainy days. But my dad would take us outside in the backyard with his telescope, and we'd look at the heavens. And having grown up in a Christian family, it was always with the understanding that God was the source of all this wonder that we were looking at. But it brought up a lot of questions, and probably similar questions to ones that you've asked, as well as humans throughout history. Things like, how big is all this? When did it start? How long's it been here? Is there anyone else out there? And those kinds of questions. So again, as I mentioned, I grew up in a Christian environment, both at home, and we went to church on a regular basis and were very active in our churches. But I attended secular schools over the years, all the way from grade school through grad school, in the Pacific Northwest. Did my undergrad at Willamette University in Oregon, and then Stanford for grad school. And I heard over and over again in my science classes, starting as young as junior high, that the facts of nature that we were studying had nothing to do with God or religion. And even as a little kid, that just didn't make sense to me. Was there a question or audio problem?
No, we thought we had a problem, but we don't, so it's good.
Okay, good.
Sorry.
No worries. But anyway, even as a kid, the idea that God and science might be incompatible just didn't make sense. I thought, if God is the creator of all the wonder and all of the amazing things that we see in nature, if he's the God of creation that we read about him being in scripture, then how can his actual handiwork contradict who he is? It just didn't make sense. And so from a fairly early age, it kind of set me on the path of trying to figure out how science and faith fit together. But I must say, I took a few detours along the road. I started out as a political science major at Willamette. I had always heard, all my teachers in high school and grade school had told me, you're really good in math and science. You really ought to major in math or science. And at that point, my perception of there being a conflict between science and faith was really strong. And I just didn't have the tools to figure out how to reconcile the two fields. And so I took a lot of math and science as an undergrad, but I majored in political science. And God has a sense of humor because after I actually my senior year at Willamette studying political science, I did an internship at the State Department in Washington, D.C. And very quickly realized that in order to get anywhere in the State Department, I needed an advanced degree. And this was back, I'm going to date myself, this was during the Cold War. And so our arms control negotiations was one of the very prominent things that the State Department was involved with. And so I thought, gee, if I could get a technical degree in aerospace engineering, which was a field that I'd considered earlier on, wouldn't that bring something good to the table in terms of being able to understand how the various weapons systems that the State Department was negotiating over actually functioned? And so, naive little 22-year-old me, I applied to Stanford for a master's program in aerospace engineering, not considering the fact that, gee, I don't have an engineering undergrad degree. And lo and behold, again, for me, I think it was a divine intervention, but they admitted me. And so I will say that it was one of the hardest things I've ever done, sitting in classes with surrounded by people that already had an engineering degree and trying to, compete for grades. But God was with me and got me through it. And from there, I got really interested in the space program and didn't actually go back to the State Department, but started working on NASA programs such as the Hubble Space Telescope and the International Space Station program. And I was supporting astronaut simulations of working with the hardware for both the space station and the Space Telescope, primarily neutral buoyancy simulations. But along the way, I ended up getting a lot of astronaut training myself. And before too long, Lockheed designated me as their corporate astronaut. And then, of course, there were the two shuttle accidents that intervened, so to speak. And the political situation got very uncertain. And I was still supporting the different programs, but as I mentioned, NASA went through a pretty serious lull after the two shuttle accidents, And I got, quite honestly, kind of tired of sitting around waiting for my chance to fly. And that was actually when I got recruited by a fellow Stanford grad to work on the Bellagio fountains, which dealt with hydrodynamics as opposed to aerodynamics. But there were a lot of crossover in terms of skills. So I was in charge of R&D for the Bellagio fountains and the programming system that we set up to program the choreography on the fountains. Also along the way, I did a lot of work with both the RAND Corporation and the Aerospace Corporation on both NASA and Air Force projects. Then after I worked on the Bellagio fountains, I crossed paths with a guy at my church who was a music director, and he was teaching at Azusa Pacific University and recruited me to fill in for one of his colleagues in the math and physics department. And so that really spoke to my heart and really felt like God was calling me to help these students wrestle through issues related to science and faith, the same ones that I'd wrestled through myself as a student and beyond. And so I had been teaching astronomy and other physical science classes at Azusa Pacific for a number of years when in 2014 there was big breaking news in the astronomy world about possible evidence for the gravity waves that Einstein had predicted. And so the PR office at Azusa Pacific reached out to me and as an astronomy professor and said, hey, would you be willing to talk to a few media outlets about a Christian perspective on possible evidence for these gravity waves? And so I talked to a few different places and gave interviews, and then they came back and they said, could you write a piece for CNN's Belief blog about this? And so they gave me about 24 hours to write this thing. And so I finished it off after astronomy class that night, and the CNN editor titled it very provocatively as "Does Big Bang Breakthrough Offer Proof of God?" Now, you may have the same reaction to that as I did. As both a Christian and a scientist, I'm very, very careful with the use of that word proof because there's so much baggage that comes with it. But the CNN editor titled it this way, more or less as clickbait. And the piece went viral. It had over 500,000 views within less than a week, and over 70,000 shares on Facebook. It was in the top 5 worldwide most shared news stories on social media. So it garnered a lot of attention. And in the wake of that, that publicity, I was then offered a book contract to write a book about connections between science and faith, which is available on Amazon. It's called God of the Big Bang: How Modern Science Affirms the Creator. But the email response and other types of response that I got, the public reaction, both from this CNN article as well as when my book came out, very much underlined the need for a more civil dialogue about science and faith as opposed to this very polarized response, which of course we're seeing all over the place in culture today. But one of the places that we see this most in the science and faith dialogue is when it's portrayed by what I would refer to as extremists at kind of opposite ends of the dialogue. People who fully reject religion, people like Bill Nye, the science guy, who rejects religion, and people who like Ken Ham and others that try to kind of conform science to fit their view of biblical interpretation, which usually tends to be a very kind of fundamentalist view of how scripture must be interpreted, with literal 24-hour days in the Genesis account and accounts of genealogies that can be used to show that the time that's elapsed between Adam and the present day, or Adam and Jesus, is a relatively short period of time, rather than a more nuanced and scholarly approach to biblical hermeneutics. So there's this illusion of conflict. There's no question about that. But I would say that it's really more of a conflation of concepts that don't have to go together. So on the one hand, where we have, let's say, Bill Nye's position, or somebody like Bill Nye, that would say that full trust in science, really a scientism, which puts this real faith in science as opposed to looking at science as a process for discovering truth. So the position of full trust in science, full trust in the process of evolution to get from molecules to man, so to speak, without God in the picture, really leads to this scientism, which is, like I say, a wholehearted faith in the ability of science to explain everything, together with a secular worldview. And then on the other hand, we have the position that trusts in religion, Christian or otherwise, with a very sudden view of creation, with God behind it, and a mistrust of science that leads to a position that is commonly referred to as creationism, which is a fast creation, very recent, coupled with a Christian worldview. And these two extreme positions would lead to a very real perception of conflict between those extreme positions. But if we look at science as a process for discovering truth about God's creation, then there's room for dialogue, and we can have conversations that include both science and faith in a very healthy and productive way. So anyway, that's all. That is by way of background for the talk tonight that you really came to hear about, which is about the anthropic principle and whether planet Earth is just a lucky accident. So this anthropic principle is also known as the Goldilocks principle, which is basically the idea of, everything being just right. Just like in the story of Goldilocks and the Three Bears, we have everything that is just right. It's not too hot, not too cold, not too big, not too small. And so those two terms are more or less interchangeable. The anthropic principle says that there seems to be a long and growing list of universal parameters that have to be just what they are in order to have life anywhere. And this goes hand in hand with the teleological argument, or the argument from design for the existence of God, as well as the fine-tuning argument, which again is very similar to the anthropic or Goldilocks principles, which talk about how everything has to be just finely tuned to the values that they are. Otherwise, the possibility of life cannot exist. So let me move on. One interesting thing, I'll try to circle back to this later, but it's kind of the odds of getting everything just right, and I will circle back to that a little bit later, but that's the reason for the lottery balls. Okay, so let's talk through some of these parameters. So for example, if we start out with Earth's location, its distance from the sun is just right. It's not too hot, not too cold. Well, I'll come back to some examples with Mars and Venus that very clearly illustrate if we go too far from the sun, we get a frozen world like we see in Mars that barely warms up to non-freezing temperatures during the summer season near the equator, but otherwise has most of its water frozen. Versus Venus, the other direction, which is much hotter. And like I said, we'll circle back to those examples in a little bit. So the Earth is also just right in terms of its size and its gravity. So Earth's size gives rise to the amount of gravitational pull that it has, which is related to the amount of atmosphere that it can hold on to, as well as its heat retaining. Well, the atmosphere gives the heat retaining characteristics. So Earth's gravity is just right to keep the thin layer of gases above us. And in this photograph, I don't know how well you can see it, but you can see, hopefully, what's referred to as the thin blue line of Earth's atmosphere against the edge of the Earth seen from space.
Yep.
Yeah, good. I'm glad you can see it. And Earth's atmosphere acts as an insulating blanket. It protects us from harmful radiation, and it's the perfect composition to support life. One really cool thing about Earth's atmosphere and its gravity is that Earth's gravity is just exactly what it needs to be to hold on to large amounts of water vapor at 18, let's see, is that right? 18 grams per mole. But not strong enough to hold on to large amounts of either methane or ammonia at 16 and 17 grams per mole. So that dividing line between 16, 17 grams per mole for these poisonous gases of methane and ammonia versus water vapor at 18 grams per mole is pretty amazing. You know, if you tweak Earth's gravity at all, if it becomes a little bit stronger, then you hold on to lots more methane and ammonia, which would poison us. Or if it's a little bit weaker, we don't hold on to enough water vapor, which is part of the life-giving water cycle. So that's one, to me, that's one of the most amazing things is how Earth's gravity, Earth's mass and its gravity are just balanced on this knife's edge. Okay, moving on. Earth's composition and magnetic field are also just right. We have a metallic liquid core that moves around, moving electrons that are found in these metals in the core give rise to the magnetic field of the Earth, which also protects us from the deadly solar winds. And it preserves the atmosphere rather than having the atmosphere gases susceptible to being stripped off by the charged particles from the solar winds. And here's another neat fact, is that Earth's magnetic field enables migration. And I don't know if you guys have thought about this much, but the migratory animals like whales, dolphins, homing pigeons, you name whatever migratory animal, they have magnetite in their brains. And that magnetite actually lines itself up in their brains within the magnetic field, just like a compass, and enables those animals to reliably navigate, which is kind of mind-boggling. And at the Earth's north and south poles, we get some of the solar wind particles that creep through the magnetic field and give us this beautiful reminder in the auroras of the purpose of that magnetic field in protecting us and our atmosphere. Our atmosphere is also just right, with 78% nitrogen and 21% oxygen and about, roughly 1% of various trace gases. If we had more oxygen, everything would burn faster, as well as, when I say burn faster, it's even our metabolisms would speed up, and our bodies would age more quickly if we had more oxygen in our atmosphere. And again, we'd have more fires. Every single thing we look at has to be just exactly what it is in order to get the life-friendly atmosphere and environment that we have here on Earth. Also, we have the ozone layer, which keeps us alive by absorbing dangerous radiation from space. So a number of years ago, I'm sure that you probably were aware that scientists were very concerned about the growing hole in the ozone layer. And with the reduction of use of CFCs and other harmful chemicals, we've been able to actually heal that ozone layer. So it's not as big of a concern now. Of course, we still need to be careful. But if we had more of the high energy UV radiation coming in from space, we would have, again, we as living beings would absorb more radiation, which is, of course, instrumental in cell mutation and tumor formation, including various forms of cancer. If we had more ozone, then we would have less radiation reaching the Earth, and that would interfere with plant photosynthesis. So again, here we have this fine balance between, not too much and not too little. Carbon dioxide in our atmosphere is, obviously everyone knows by now that carbon dioxide is a greenhouse gas, and so it helps us to retain some heat in the atmosphere. We also have the ability to retain water vapor in the atmosphere, which of course is not only a greenhouse gas and helps that warming of the Earth's atmosphere, but it also delivers rain as part of the life-giving water cycle. And this is kind of an interesting fact that maybe people don't think about too much, but we have an average of 1 lightning strike per second on this, somewhere on this planet. And lightning serves a useful function of fixing nitrogen into nitrates that serves as a fertilizer for plant life on Earth. The rotation of Earth is just right also. We have a rotation rate of once per 24 hours, as everyone knows. If we had a slower rotation rate, we'd have more extreme temperatures, both at daytime and at nighttime. If we had a faster rotation, the tropics would become warmer and the poles colder. So either way, we'd have different climate extremes than we do, and less habitable area. Another thing is the just right axial tilt. The 23.5-degree tilt on Earth's axis gives us seasons, as opposed to if we were just straight up and down North Pole and South Pole, perfectly perpendicular to the orbital plane. And that, of course, gives us seasons, and it actually doubles the amount of available farmland because of those seasons. We also have a just right water cycle. Earth's the only place that we know of with water that exists as solid, liquid, and gas, which is necessary for life. And it's kind of interesting because when we get reports from NASA about looking like at extrasolar planets around other stars, one of the first things you always hear about is there liquid water? But the reality is we need water that it is capable of existing in all 3 physical phases to give the life cycle, the water cycle, because essentially, let's look at Mars, for instance. As soon as some of the water ice freezes on Mars, it melts, but because of the low atmospheric pressure, it immediately evaporates. And then once it evaporates, because the gravity of Mars is only 3/8 of what Earth's is, we just talked about the perfect gravity of Earth to hold on to water vapor. Mars can't hold on to water vapor, so it escapes into space. So you need to have water capable of existing in all 3 physical states. So you've got to have liquid water, you've got to have gaseous water, water vapor, and you might not think too much about the solid water, but the solid water that we have in our ice packs in glaciers and at the poles serve as water storage systems. And so we have large reserves of water in these glaciers and in ice caps. So it's necessary to have the correct conditions, not just temperature wise, but also atmospheric composition and gravity wise, to give or to allow water in all three physical phases in order to have the water cycle. So our moon is also just right. If it were bigger or closer, its gravitational pull on the Earth's waters in particular would cause tidal waves on a regular basis, submerging continents very regularly. If it were smaller or farther out, then the tidal pull wouldn't be strong enough to give us the tides that we have, and the shoreline waters across all the oceans would stagnate. And another interesting thing, as some of us might be looking forward to the upcoming solar eclipse that's happening in April, is that the moon is just the right size in our sky, that the sun is exactly the same size as the moon is in the sky because of the ratio between its actual size and distance, that we get these perfect solar eclipses, which enable us to study the sun in a better way than we could before and be able to see the corona. And so that's, I mean, it's just like a gift, you know. I mean, it's not something that we need for our survival, but for our intellectual curiosity. And I'm reminded of a verse in Proverbs, and I can't think of the exact reference offhand, but it talks about it is the glory of God to conceal a matter, and the glory of kings or humans to search it out. And I love that interplay. God has given us certain mysteries to seek out and learn more about his creation, and how learning about his creation reveals who he is, as we read in Romans 1:20. And to just be able to see how lavish his love and care for us is. Our crust is also just right. The Earth's outer geological layer is 4 miles thick in the ocean basins and up to 30 miles thick under some of the mountain peaks. If it were just a little thicker, we would have less seismic and volcanic activity. We'd have less of the things that enable our crust to renew itself and to bring other minerals to the surface. If it were thinner, we'd have more seismic activity and more volcanoes, which could make life here on Earth rather chaotic. And even our neighbors in space bear the indicators of purpose. So our planetary big brothers, Jupiter and Saturn, act kind of as cosmic vacuum cleaners, sucking in various space junk that could be headed our way. And I've got a picture here of Comet Shoemaker-Levy. In 1994, some of you may remember Comet Shoemaker-Levy was coming from the outer solar region reaches in towards Earth, and Jupiter sucked it in with its massive gravity. And you see these red spots where the comet fragment struck Jupiter. And someone I was talking to referred to those spots as scars that Jupiter took for us. I just love that imagery. Each one of those scars is bigger than the Earth.
It would have hurt if it hit us.
What's that?
He just said it would have hurt if it hit us.
No kidding. That's an understatement, right? So circling back to Venus, Earth's so-called sister planet, which is just slightly smaller and a little closer to the sun, has an average surface temperature of between 800 and 900 degrees Fahrenheit, actually even hotter than Mercury, which is closer to the sun. Mercury's surface temperature is somewhere around 400 degrees Fahrenheit. But because of Venus's thick carbon dioxide atmosphere with 90 times the atmospheric pressure of Earth, it's got a runaway greenhouse effect. And so again, it's very, very hot. And as if that temperature wasn't enough and the crushing 90 times the atmospheric pressure of Earth weren't enough, It's got clouds that are laced with sulfuric acid. So that's that's about as far, size is about as far as our similarity with Venus goes. Not a very life-friendly place. And then Mars, I mentioned earlier, that's smaller and a little further out. It's too cold for water to exist for anything but a very short period of time. When it melts, very infrequently, and we get these little rivulets that have actually been captured on video from some of the spacecraft that we've sent. But because the atmospheric pressure is so low, because of the fact that it has so little gravity, the water, once it becomes liquid, almost immediately evaporates. And so again, and Mars's atmospheric pressure is only 1/100th of the Earth's atmospheric pressure. I don't know if any of you saw the first, what was it? The Total Recall, the movie of going to Mars. I know they did a remake of it. I can't remember that as well as I remember the first one with Arnold Schwarzenegger in it. But I don't know if you remember the scene where Arnold goes out without, I can't remember if he didn't have the helmet on his spacesuit or something like that. And they showed his eyes bugging out. That would be the least of your problems. In that low of an atmospheric pressure, your blood would boil. The gases that are dissolved in your blood would boil, and you'd essentially be freeze-dried very quickly. So neither Venus or Mars are very friendly places to life. And then our star, the sun, is just right. It's the perfect brightness and size and age for life. And if you change anything, the possibility of life is gone. You may have heard Hugh talk about this and how the fact that our sun is a middle-aged star means that it's in the most stable of its burning phases, which is it's essential in order to have life on the Earth. And our sun appears to be a single star for all we know, unless there's one that's way far out there on a very long orbit. But it's a good thing that our star is a single star. I'm going to show you a little demonstration of if we had a binary star system where we had, so in this diagram, we've got our sun in the middle, then we've got Earth on the blue circle, 1 AU, 1 astronomical unit away from the sun. And then on the red circle, we have a second star that's 70% of the mass of the sun. And that's 3.3 AU from the sun, or 3.3 astronomical units, or 3.3 times as far as the Earth is from the sun. Now we're going to step through this little simulation and see what happens to the Earth as we step through it. So far, so good. And I don't know if you could see that blue line, but it made a very close pass to the sun.
Yeah.
And another one. So it's starting to, I don't know if any of you guys are old enough to remember the spirograph tool or toy that you used to draw these circles. It reminds me of a spirograph drawing here. And now it's going way far away from the sun. And just guess what happens next?
Uh-oh.
And that would pretty much ruin your day. And then some, right? So we see fine tuning throughout the universe, not just here within our solar system, which is what we've kind of been focusing on, and the fact that really the Earth is the only planet in our solar system that comes anywhere close to being life friendly. But we see this fine tuning throughout the entire universe. So the velocity of light being what it is, regulates the amount of radiation that comes to the Earth. If the velocity of light were faster, we would have more radiation from all over the galaxy in particular. If it were slower, we'd have less and be able to see and study fewer neighbors in space. If the electromagnetic force were altered, it would completely alter the chemical bonding that we have. that we see in essential compounds like water vapor, for example. If the strong nuclear force were either less strong or stronger than it is, that would influence atom and element building. For example, imagine that the strong nuclear force were stronger or good for longer distances than it is. You may know that the strong nuclear force is the strongest force that we know of, but it fortunately tapers off with the average diameter of an average nucleus of an atom. Beyond that distance, it doesn't just taper off gradually like the other forces do. It goes from being the strongest force that we know of to zero at the edge of the atom's average diameter. And if that were not the case, imagine this force that acts between neutrons and protons overcoming the electromagnetic force. If it were good for longer distances or any stronger, or a combination of both, then you can imagine that all the neutrons and protons in a specific area would all be stuck together in one gigantic mass. Or if the strong nuclear force were weaker, the only elements that you could have would be hydrogen, because it wouldn't be strong enough necessarily to overcome the electromagnetic force of proton to proton. So you couldn't have more than one proton in a nucleus. So the strong nuclear force is exactly what it needs to be to give a life-friendly universe. The expansion rate of the universe, if it were faster, it could prevent galaxy and star formation, let alone planet formation. If it were slower, we could have already experienced the quote unquote big crunch with gravity overcoming the expansion rate and all of the material in the universe collapsing into itself. The mass density of the universe, similarly, if the mass density were greater, we could experience the big crunch or collapse. If it were lower, then you'd have this accelerating expansion that could be too fast to have galaxy and star formation, and again, let alone planets forming. And then there are the physical laws themselves, which govern all these different processes and interactions between space, time, matter, and energy. And Lydia Jaeger, who's a physicist and academic dean at l'Institut Biblique de Nogent-sur-Marne, I'm calling on my high school French, and author of Cosmic Order and Divine Word, writes, "The law-like regularity and consequent modelability of natural phenomenon are the unquestioned assumptions that underlie all scientific research." In other words, you have to have this regularity and modelability in order to have the predictability and be able to test your predictions and count on the consistency of these laws. In particular, the laws of nature are not self-explanatory. To me, they are most powerfully interpreted as traces of the creator's handwriting. I love that. I just think that's so beautiful, because I think sometimes the laws of nature get taken for granted. And it's just like, oh, well, they are what they are, but where did they come from? So as I mentioned before, the Anthropic principle, the Goldilocks principle, the fine-tuning principle, all of these go together and get at the same thing, essentially. Paul Davies, astrophysicist from Arizona State, writes in the Cosmic Blueprint, "The impression of design is overwhelming. It seems as though somebody has fine-tuned nature's numbers to make the universe." And Sir Fred Hoyle, in his book, The Universe, says, "A super intellect has monkeyed with physics as well as with chemistry and biology." And these are kind of quotes from atheists, or not necessarily atheists, but maybe agnostics. I don't know. I have a hard time believing that Paul Davies is not some form of theist. I'm not sure that he's a Christian. I have not ever seen a profession of faith from him, but it's hard to look at these and not read that gee, it'd sure be a lot easier if we had this super intellect that we could pinpoint as the cause for all of this fine tuning that we observe. So let's just, talking about Earth, we've gone over all these things that make Earth this amazing place that it is, but is it just a lucky cosmic accident? We've gone over all these different features. You might think, if you're looking at this from a purely naturalistic perspective, that you could find one of these attributes that could be improved upon somehow. If it was all just this, lucky random accident, then surely we could find something that we could improve on. But we look at each one of these parameters, and even the ones that we looked at throughout the entire universe, and if you tweak any single one of them, even by a very small amount, it decreases the likelihood of life existing or continuing to exist, not just on Earth, but anywhere. And Genesis 1 verse 3 says, and God saw all that he had made, and behold, it was very good. And I love that, throughout the Genesis 1 account of creation, at every stage of creation, God comes back and says, and it was good, and it was good. And he gets to the creation of man, and it was very good. And I just love reading Genesis 1, the account of creation. There is such a beautiful thing, and other passages of scripture that talk about it. And just, the more we learn from science, the more we see this deep compatibility. And I go back to Romans 1 verse 20, the truth about God can be seen in what he's created. And some people might look at that and say, yeah, okay, I'll give you that, we can see God's power and his might through creation, through what he's created. But looking at all these characteristics that we've gone through, the elements of the anthropic principle or the fine-tuning argument, to me, it speaks to a God of love, because he's created this place where not only can we just barely survive, we're not some biology experiment where, we're struggling for each breath. We're not just on the edge of being able to survive. We're in an environment where we can flourish and thrive. And to me, that speaks to a God of love. So I mentioned the odds earlier. The first things that we looked at there were 9 life-supporting design characteristics through that we could look at on Earth in comparison with the other traditional 9, I guess I should say the 8 planets of our solar system now, since Pluto got demoted. But those odds are about 1 chance in 50 million, which, that's pretty remote. But if we consider over 300 finely tuned characteristics of the entire universe, the odds are more like 1 chance in 10 to the 282nd power for life to exist anywhere in the cosmos. Now, that's a number that's really hard for most people to get their brains around, including me. And one of the things that I like to point out is that there are only an estimated roughly 10 to the 80th atoms in the entire universe. So imagine trying to pick one specific atom out of all the atoms in the universe. Your odds there would be 1 chance in 10 to the 80th, right? These odds are way beyond that. So let's move on and talk just for a minute about the multiverse hypothesis. Oops. So the multiverse hypothesis, as I'm sure most of you know, is that there may be an infinite number of separate universes, each with a different set of physical laws, and that our universe may or may not be the only one to have gotten all the numbers just exactly right for the physical laws and physical parameters in order to support life. But let's just go back to that probability for 1 minute. So if there are 10 to the 80th atoms in the entire universe, let's not say there are an infinity of additional universes. Let's say there's 10 to the 80th universes out there, okay? Even if that were the case, and there are 10 to the 80th atoms in each one of those, picking one specific atom out of that 10 to the 80th universes would still only be odds of 1 chance in 10 to the 160th power. And we're still not even close to that 10 to the 282nd power that we have to consider if we look at the anthropic principle and all the different finely tuned characteristics. Actually, I believe it was one of my friends at Reasons to Believe who did to put together kind of an analogy for those odds. And they said, it's like one person just buying one lottery ticket each time they play the lottery and winning on the one ticket that they buy each time, twice a week, every week, for 50 years in a row. So I use that analogy sometimes with my students, and I say, you know, what if you read a newspaper article, not newspaper, nobody looks at a newspaper anymore, but an internet article that said that someone had done this, that someone had won the California lottery twice a week, every week for 50 years in a row on the one ticket that they bought each time. I mean, my students will always come back and say, you know, I would say that it had to be rigged. And I say, bingo, it's exactly right. You can say the same thing for the universe. The odds are stacked against having any place in the universe that we could survive in, aside from somebody rigging it. So I know this slide is probably impossible to read, but I love the photographs. I wanted to show it before I go on to the more readable slide. This is back to Paul Davies again, theoretical physicist at Arizona State. He says the degree of biofriendliness we observe in the universe seems far in excess of what is needed to give rise to a few observers. If the ingenious biofriendliness of our universe were the result of randomness, we might expect the observed universe to be minimally, rather than optimally, biophilic or life-friendly. Note too that multiverse explanations still need to assume the existence of laws of some sort, so they do not offer a complete explanation of the law-like order of the universe. Finally, invoking an infinity of unseen universes to explain certain features of the universe we do observe seems the antithesis of Occam's razor. It is an infinitely complex explanation. So if you remember Occam's razor from like your intro to philosophy class, Occam's razor basically says the simplest explanation with robust explanatory power is the most likely to be correct, more likely than a more complex solution with equal explanatory power. So Davies is saying, you know, this is the antithesis. To say, you just say, oh, well, then there's a multiverse. There's an infinite number of chances to get the numbers just right. And he says that's an infinitely complex explanation and flies in the face of Occam's razor. So that's about all I wanted to talk about. However, I do want to mention the WISH program that the Templeton grant that I got a year and a half ago is funding. The website is wishprogram.org. If you go to wishprogram.org/community, you will find a link to a survey that we're taking that's primarily geared towards supporting women. Although we welcome male participants, there's a little checkbox to indicate that if you're a male participant. But this project is in the interest of supporting women in what has historically or traditionally been a mostly male-dominated space. And so we're launching this survey that you can find at this link to find out what women's felt needs and experiences are and what they would like to see by way of support and encouragement to either join the science and faith community or to persist in it, or to get more actively involved. And so I'm hoping that the women in the audience especially will go to this link and contribute to our survey. We're really excited about the opportunity to involve more women in this space.